Okay, well, welcome everyone to the Air Seaflox System Space webinar series. Today we have Gwen Marechal from Colorado School of Mines presenting on observations and modeling of sea state gradients in the Meso-to-Submesoscale range. Gwen is a postdoc at Colorado School of Mines with Villa Villas-Boas, and previously he did a PhD in France. So take it away, Gwen.
Okay, thank you very much. And thanks for this opportunity to share my work that I have done in the Colorado School of Mines so far. So today I'm going to talk about observing and modeling sea state gradients in the Meso-to-Submesoscale range. This work is a collaboration with my advisor, Bia, with Luc Lenin from SIO and Nick Pizzo from the University of Rhode Island. This presentation is an extended version of the talk I did in Ocean Science in New Orleans. So today I have more time, so I will spend a couple minutes on application of sea state gradients in the context of Odyssey and SWOT. But before going into the detail of my result, I want to emphasize the environment in which I did this analysis. So here on the right, you have a sketch of the air-sea transition zone, which is a hotspot for air-sea fluxes between the upper ocean and the lower atmosphere. The waves are the physical interface of the two media, and they have the potential to modulate those fluxes, and therefore the amount of heat, momentum, and mass that you can find in the atmosphere and in the ocean. Also, all the variability experienced by the wave field have the potential to have feedback into the atmosphere and the ocean. For example, it can modify the drag coefficient or the mixing of the upper ocean. And today I'm gonna focus on this bottom part of this triad, the interaction between waves and currents. On this slide, I'm showing a couple examples of wave-current interactions. So the first thing to notice is those interactions are reciprocal. The waves impact the currents and the currents impact the waves. For the waves effect on current, the bottom part of this slide, when you have a wave field, you have a new term in your surface dynamic. We call it the Stokes drift. And these Stokes drift have the potential to modify the mixing and the mixed layer depth in the upper ocean, and also enhance the surface current gradients as shown by Delphine with very high resolved oceanic model. Also, currents have effect on waves. So, for example, currents can modify the sea surface roughness. This is the reason why you can observe short scale features in SAR images or single images because of this the modulation of currents on the short waves. Also, currents can enhance the braking, so you can observe wave braking even in a field where you don't have wind. As I said, when you have waves, you have a Stokes drift, and in the presence of surface current gradient, it might be possible that there is a special variability of the Stokes drift as well. And finally, the currents affect the sea state, and this is the point that I will present today. And this topic has regained interest since a couple of years now because of its potential effect on the accuracy of sea surface variable retrieval from space, for SWOT, for example, and also for its potential to impact the coupling between the upper ocean and the lower atmosphere. So this is where my work starts. So for several years now, the air-sea interaction community have recognized that short-scale current can have large effect on the sea state. As an illustration of this statement, I am showing you two maps here of the significant wave height simulated with WaveWatch in the California current region. On the left, you have a snapshot of the significant wave height when I force the model with current, and on the right, a simulation without current. And you can see that you observe a special variability of the significant wave height from the mesoscale down to the scale where the surface current gradient are effectively resolved, which is not the case for simulation without current. So on the left figure of this slide, you have the same result, but in the Fourier space. So you have two wave number spectra that gives you the distribution of the variance of the significant wave height across the scale from the mesoscale down to the submesoscale range. You can see that the simulation with current in the dark green is more than 1 order show variance more than 1 order of magnitude than simulation without current, which is shown with this red spectrum. And we have, so far, we have some evidence of the spatial variability of the C state, but only in the mesoscale range from altimeters, among others. At shorter scale, because at shorter scale, we don't know what looks like the spatial variability of the C state because we don't have sufficiently resolved observation to observe them. So for example, with altimeters at scale shorter than 50 to 30 kilometers, most of the backscattered signal is drawn in the instrumental and geophysical noise. That statement motivated us to use airborne LiDAR in order to observe the spatial variability of the C state at shorter scale. So the concept of airborne LiDAR observation is provided on the left. So this is an animation of the concept of airborne LiDAR observation from an airborne LiDAR simulator that I have developed. So you have a wave field propagating from the left to the right. The LiDAR is carried by an aircraft, and then it retrieves the sea surface height with a pixel size of order 100 meter. And from the variance of the retrieved sea surface height, you can compute the significant wave height at the desired spatial resolution. Most of the observations that I will present today have been collected from the Submesoscale Ocean Dynamic Experiment funded by NASA. The experiment took place offshore the Bay of San Francisco between 2021 until 2023, so in April last year. Okay, so let's look at observation now. On the top, you have a scatter plot that shows you the spatial variability of the significant wave height. The significant wave height has been computed from sea surface height in a segment of 2.5 kilometers of sea surface height retrieved from the airborne LiDAR. And the first thing that you can see in the scatter plot is how random is the spatial variability. We don't observe a coherent patterns as expected from numerical simulation. And at that point, I was like, okay, there is certainly something wrong. So perhaps I need to go back in the data processing. Perhaps there are a lot of unexpected noise. But actually, when I came back to the SSH field, so the retrieved signal from the airborne LiDAR, I saw that most of the swath was occupied by a succession of high crest and deep troughs, so wave packets. And because the airborne LiDAR resolve individual waves, the airborne LiDAR also resolve wave groups, and those wave groups seems to have impact into the significant wave height, and also impact the sea state variability at the kilometer scale. So here in this animation, every dot is one significant wave height, and you have the associated sea surface height field. So from the variance of this signal, you have one value of the significant wave height. And those gradients can reach almost, for that observation, almost 3 meters in 2.5 kilometers because of those presence of wave groups. So in airborne LiDAR observation, we do observe a background and unmodulated significant wave height, plus a potential modulation induced by an underlying current, and also a modulation induced by the wave groups. And one question that I asked to myself is, what are the spatial scale where those wave group induced modulation occur, in order to know if it's possible to consider a longer segment length so that the effect of wave groups are mitigated, and I would be able subsequently to observe the current induced modulation. So in order to answer this question, I had to create a new framework where the current induced modulation are not taken into account. So for that, I created synthetic sea surface height field. So you have an example here on the left. So this synthetic field has been inverted from realistic wave spectrum. In those synthetic fields, there is no current-induced modulation. And what I was trying to do with this experiment is to reproduce what synthetic airborne LiDAR observed for a given synthetic wave field. So for a given spectrum with a given unmodulated HS, I inverted synthetic sea surface height for a bunch of different spectra. And when I start this animation, you can see that you observe a spatial variability of the significant wave height. So the colors of the rectangle are the value of the significant wave height. And we do observe something similar as the observation provided from the airborne LiDAR. So this is one realization for a narrow and very peaked wave spectrum. This is another experiment when the wave spectrum is broader, but the unmodulated HS is still equal to 6.2 meter. We do observe this special, we still have a variability of the spatial variability of the significant wave height at the scale where the significant wave height is computed. And here I'm showing a third example where when the wave spectrum is very broad. And what I want to emphasize here is the shape, the spectral shape is key for the intensity of the wave group induced modulation. You can note that all the HS for the three spectra here is the same. So the mean HS is equal to 6.2, but the spatial variability is definitely stronger for narrow banded wave spectrum. And this is expected because the wave groupiness is stronger when you have a narrow banded wave spectrum. The waves have more the tendency to organize themselves into groups. On this slide, I'm showing to you the answer to the question, what are the spatial scale where the wave group induced modulation and HS occur? So on the x-axis, you have the peakness parameter, which is an indicator of how narrow and peaked is your wave spectrum. And on the y-axis, you have this quantity, I call it LWG, which is the larger scale where the wave groups impact the significant wave height. So the first result that you can see from this plot is the scale where the wave groups impact the significant wave height is longer when you have a narrow banded wave spectrum. As I said, this is expected because the waves are more the tendency to organize into groups when you have a narrow banded wave spectrum. And you have the opposite result, like you have a shorter scale, a smaller value of LWG for broader wave spectrum, and because the wave group induced modulation is smaller than for narrow banded wave spectrum. And the second result and I think this is the main takeaway of this presentation, is when you look at those spatial scale where the wave groups impact the significant wave height, you can see that we are in the same range of the range where the main source of variability of the significant wave height was expected, driven by surface currents. So here we do observe two sources of spatial variability of the significant wave height from two different processes, but at similar scale. One from currents and another one from the wave groups. So at the beginning, if you remember, I wanted to use airborne LiDAR to observe short scale variability of the sea state. So with altimeter, we were limited in space because of the instrument. But now with the airborne LiDAR, we have to deal with a new source of modulation coming from the wave groups because airborne LiDAR resolve individual waves. So we are still not able to observe that kind of spectral slope or to observe current-induced modulation in the submesoscale because those modulation can be overshadowed by group effects. So, but even if those current and wave groups occur at the similar spatial scale, they do not occur at the same temporal scale. So there is possibility to capture persistent current effect on the sea state and mitigate the effect of the wave group. The idea is to use still airborne LiDAR, but when the aircraft was scanning the same sea surface within a sufficiently number of passes, then because the group effect on the significant wave height seems to be shorter lived than the current effect. So you would be able to capture persistent current effect if you consider sufficiently number of passes. The idea behind is to scan the wave groups at different phases. So for one location, if you consider sufficient number of SSH and HS observation, you can average all the HS together, and you should be able to capture a local HS without group-induced modulation. This is the idea of the strategy that I used to observe persistent current effect on the sea state, and this is one illustration of this strategy. So on the left, you have an animation of the airborne LiDAR observation. So the aircraft is scanning the same sea surface 8 times. On the right, you have the evolution of the significant wave height along the latitude. You can see that we have very sharp significant wave height gradient between 2 successive observations because of the presence of wave groups. It is not possible to see any coherent patterns in those measurements. But once you average all those observations together, this is what you get. So the panel on the right is the mean average observation from the example I was showing to you in the previous slide. The top figure is the location of the observation. The arrow, the white arrows gives you the dominant direction of the incident wave. So you have one observation quasi along the dominant wave direction and quasi across the dominant wave direction. On the bottom panel here in red is the mean average HS for across wave sampling. And the thing that you can see in those two plots is we do observe a spatial variability of the sea state at different scales. For example, for the panel on the right, you can see an increase of the significant or a decrease if you start from the bottom, but a large scale significant wave height gradient at 80 kilometers. So between here 0 and 80 here. And on the bottom, you can observe shorter scale spatial variability of the significant wave height with different intensity. So for example, here at a scale of 10 kilometers, we observe a variability of the significant wave height induced by current, which is equal to 3%. Yeah, something that I didn't mention, for those observations, the wind is stationary. So there is no local wind change throughout the observation, according to the ERA 5 product. So perhaps if we look at higher resolved observation, we would see some area, some change of wind. So here, yeah, as I said, you observe spatial variability of the significant wave height at different scales, so 10, 15, 25 kilometers in the example that I'm providing here. Those spatial variability cannot be resolved with altimeters because of the dominance of noise at those scale. So here we have a proof that we observe a spatial variability of the sea state in the Meso-to-Submesoscale range. Another interesting result is when I superimpose the blue line with the red line, you can see that the spatial variability of the significant wave height for across waves observation occur at shorter scale than for the observation performed along the wave direction. And this anisotropy of the spatial variability of the significant wave height is something expected from a numerical result, for example. So here I am showing to you the same figure that I was presenting at the very beginning. So you have the incident waves coming from the northwest. So if you sample the significant wave height along the dominant wave direction, you will capture large scale gradient. But if you sample the significant wave height across the dominant wave direction, you would capture shorter scale variability. And this anisotropy of the significant wave height have different applications. And one among others is for SWOT, for example. So for people here in this audience who have heard about SWOT measure the sea surface height within two 50-kilometer swaths. And the performance of SWOT to capture the sea surface height depends on how you correct the effect of the sea states through the sea state bias correction. So for example, and there is one correction which is based from the nadir observation. So the community take the sea state bias at the nadir and then propagate the sea state bias throughout the 250-kilometer swaths. But if you measure the significant wave height along the dominant wave direction, you will capture large-scale gradient, and then you will propagate those large-scale gradient across the two swaths. But you would expect shorter scale gradient within the two swaths because of this anisotropy of the spatial variability of the significant wave height. Yeah, and driven by the current, by the way. Okay, so this is my summary slide for this analysis. We have motivated this work because the spatial variability of the C state has the potential to modify the RC fluxes and the amount of momentum, heat, and mass in the atmosphere and the ocean. We have used airborne LiDAR observation to reveal C state gradient at scale unresolved by altimeters. So from the 100-kilometer scale down to the scale where the significant wave height is computed. We have seen that we have two different sources of spatial variability of the significant wave height, wave groups and surface currents. And the wave groups effect seems to dominate the effect of the currents at the kilometer scale. So those effects can overshadow the current effects. Yeah, and they occur at similar spatial scale. There is some strategy that has been used to mitigate the effect of the wave groups to observe persistent effect of the current by leveraging the temporal scale separation between the two processes. Something that I didn't mention, I think it's important to mention it. For this example, between the very first observation and the very last observation, so after 8 reciprocal passes of the airborne LiDAR, you have an interval of 3 hours. But in 3 hours, your underlying current can change, move, or go somewhere else, or change its dynamic. So it could have impact into the C state gradient by shifting or smoothing the retrieved spatial variability of the significant wave height. So that's something that we have to keep in mind if we want to interpret some spatial variability of the significant wave height at some mesoscale range. Yeah, so that's something that we have to keep in mind. So this is the end of the first part of my presentation. And after, I will talk about applications. So is there any question so far?
Questions at this midpoint? Maybe people are going to save questions for the very end.
Okay. Okay, so let's move forward. So for the next part of this talk, I will talk about 2 different contexts of where the C state gradients can have significant effects. So the first one is for SWOT. So we have seen from the first part of this presentation that currents, we do observe a spatial variability of the significant wave height in the meso-to-submesoscale range. In SWOT, the effect of the waves of the C state impact the performance of the sea surface height retrieval in the meso-to-submesoscale range. So there are some correction based on the significant wave height on the wind speed to correct the effect of the C state in order to have more accurate SSH observation from SWOT. One strategy to correct the C state bias in SWOT observation is to use nadir observation and propagate the C state bias from the nadir throughout the 2 swaths of SWOT. On the right, I am showing to you one plot. So the background, you can see the footprint of the SWOT satellite. You have the 250-kilometer swaths. The nadirs are shown with those dots in the middle. And on the right, you have a map, an objective map of the significant wave height. So the data have been collected. So those are airborne LiDAR data that have been collected during the SWOT Calval last year. So the SWOT Calval took place actually during the IOP2 offshore the California current. For this objective map, I have used a special scale for the interpolation that are sufficiently large to average the effect of the wave groups. But you can see that for one azimuth of the satellite, you observe a special across track variability of the significant wave height. So if we use the correction based on the nadir to correct the C state bias throughout the SWOT swaths, we would undercorrect the C state effect on the SSH, because you won't take into account the spatial variability of the significant wave height that occur at scale of the SWOT widths. For example, here at the nadir, we measure 3.5 meter, HS equal to 3.5 meters, which is actually, I will show you later, these observations are pretty consistent with the altimeter. And that at far range, we observe HS equals to 4.5 meters. So there is a gradient of 1 meter in 50 kilometers that might have impact on the accuracy of the SSH retrieved by the satellite. Here I am showing to you the same observation. So on the left, you have the objective map of the significant wave height. You have the nadir observation from SWOT on the left edge of the objective maps. In the middle, you have the C-state bias. So from the HS provided, the HS observed from the airborne LiDAR, we look at the lookup table provided by Curtis at JPL, and we computed the C-state bias for a given wind speed, actually. The C-state bias depends on the first order on the HS, and there is some modulation of this C-state bias according to wind speed. And on the right, you have the uncorrected C-state bias. So in this very last plot, when the dots are white, it means that the C-state bias computed at the nadir is identical to the C-state bias computed at different ranges of the SWOT satellite. Okay, so you can see that we have a special variability of the C-state bias that could have effect on the accuracy of the SSH. And to emphasize this point, here I have highlighted an area with this dashed black circle. This area has a diameter of 30 kilometers, and you can see that we have an uncorrected C-state bias because of the special variability of the C-state that reach almost 2.5 centimeters. And those gradients of 2.5 centimeters are in the same range of the SSH gradient that SWOT aims to map. So those special variability of the C-state have the potential to hide some mesoscale features within the SWOT swath. So this is one example from mass observation. And then here I want to present another example, but from SWOT observation. Sorry, when I said mass observation, this is the name of the package that carries the airborne LiDAR. Okay, so this is one example from SWOT observation. So I took a specific transect that crossed the Agulhas current. In A, you have a map of the significant wave height. Something that I didn't mention is this SWOT provide a significant wave height product within its two 50-kilometer swaths. So you can observe here, we have an enhancement of the significant wave height in this chunk of the SWOT swath. In panel B, you have I have plotted the C-state bias correction based on the nadir observation. So that's why you have those zonal structure. So you, as I said previously, from the nadir observation, you have one value of HS. You have values of HS, observation of HS on wind speed. Then you go to the lookup table, you compute one C-state bias, and then you propagate the C-state bias on both sides of the nadir. In C, you have another correction which is based on model. So here the community run a spectral wave model like WaveWatch and force with only wind, and then from HS simulated from the model, you go to the lookup table and then you compute a C-state bias. You can see that we don't see any special variability of the C-state bias in this correction. That is to say, there is no current forcing. If we had current, we would be able to see some special variability within those two SWOT swaths. In panel D, so this is a map of still the C-state bias, but based on the local significant wave height observed by the satellite. I call it my correction for the next part of my presentation. So you can see that we do observe maximum of C-state bias where we have an enhancement of the significant wave height. Actually, the accuracy of the significant wave height observed by SWOT is still in discussion, but for this example, I will assume that we have the true significant wave height, but we can discuss it during the Q&A session. Panel E on F are the difference between the correction based on the nadir on my correction and the correction based on the model on my correction. And if you look at the panel E, if we go to the area where there is an enhancement of the significant wave height, so here around 33 south, you can see that we have an undercorrection of the C-state bias up to 3 centimeters, which is significant. So that have an effect on the accuracy of your of the SSH retrieved by the satellite, but also for geostrophic currents. And speaking of geostrophic currents, here I am showing to you one application of this correction based on the HS observed by the SWOT. So the background arrow are the large-scale Agulhas currents. So you have this southwestward branch, the main branch of the Agulhas current. You have the retroflexion that flow from the west to the east. And here you have 150-kilometer swath, so the left one, actually. The left swath. And you do observe some geostrophical fronts with a velocity of 1.5 meter per second, for example, here. This is where we observed the enhancement of the significant wave height in the previous slide. And in the middle, this is the current speed, the geostrophic current speed, but based on my correction, so based on the local HS. And the last panel is the difference between the panel in the middle and the panel on the left. And you can see in this last panel that most of the swath is red. So that is to say that my correction provide stronger geostrophic current. So yeah, here I repeat, I have assumed that the HS observed by the carrying antenna, like at off nadir, at different range, is accurate. So yeah, we have a swath that is mainly red. And if you look at this area where we observe the enhancement of the significant wave height, we do observe a delta current speed almost equal to 0.5 meter per second, which is significant. And there are some cases that I looked at where this difference is even stronger. So for this first application, here I am summarized what I've done through 3 key questions. We have seen that we have a spatial variability of the significant wave height within the SWOT swath based on the airborne LiDAR on the SWOT observation. In the near future, I want to quantify those the effect of the C-state gradient within the SWOT swath in the performance of, or in the accuracy of the SSH retrieved by SWOT. Also, the second question, and that's something that we have to spend to put effort in the near future. Can we trust this HS observed by the carrying antenna? And can we base a C-state bias correction on this HS observed by SWOT? And finally, and that's more an opportunity. So if we trust the significant wave height observed at different ranges of the SWOT satellite, we have access to a 2D map of the significant wave height, which is pretty new actually. And because the spatial variability of the significant wave height capture properties of the underlying flow, it would be possible to infer some flow properties from the C-state gradients observed by SWOT. So that was my first application for C-state gradient in the meso-to-submesoscale range. And now I want to discuss the potential effect of the C-state gradient in the spatial variability of the Stokes drift. So on the left, you have 5 snapshots from WaveWatch model. In A and B, you have the significant wave height. Now you are experts, so you know the panel on the A is a simulation with current forcing. That's why you have the spatial variability of the significant wave height. In C, you have the wind speed. And in D and E, the Stokes drift, force with and without current. So the Stokes drift depends on the wave steepness. So the Stokes drift is both weighted by the wave wavelength and the wave amplitude. When you have short wave, you have steep waves, and that's why you have a large value of Stokes drift. And this is something that we can see if we look at the area circled by this dashed white circle in the Santa Barbara channel. We have a strong wind up to 12 meters per second. So in this location, we create a wind sea, so high frequency waves, very steep waves. And this is why you observe the high value of Stokes drift in the same area. But if we look at this area pointed with the white arrow, so nearby where the S-mode polygon, you can see that we have a negligible wind speed, almost equal to 0 meters per second. So when you look at panel E, so the simulation without current forcing, you have a negligible Stokes drift. But if you look at panel D, you observe an enhancement of the Stokes drift in the location where the wind speed is pretty low. So the idea behind is, in this location, we have current-induced refraction that redistribute especially the wave energy. So it creates some spots where the wave height are higher on the lower. So in this area, we have an enhancement of the significant wave height. And because the wave amplitude increase, we observe an increase of the Stokes drift. And this is what we see from the model. And those are observations. So those observations have been collected during the S-mode experiment as well. Those are 3 objective maps of the significant wave height, the mean period on the Stokes drift. The background is the large-scale current provided by the ICOM product. You can see that you have a spatial variability of the wave's properties for HS mean period on Stokes drift. And if we look at specific areas, for example, here, the area pointed with the black arrow, we have short waves. So small wave period waves are associated to short waves. So in this area, we have a 7.8 second wave, so short waves. And in the same area, we observe an enhancement of the Stokes drift, which is expected because we have shorter waves, so higher steepness, and subsequently higher Stokes drift. But if we look at this bottom right part of the objective map, you can see that you have an enhancement of the significant wave height, but the mean period is maximum. So we have long waves in this area. But we do observe an enhancement of the Stokes drift as well. So here we have the signatures of the current on the significant wave height. So we have an enhancement of the significant wave height, so an enhancement of the wave steepness, and subsequently an enhancement of the Stokes drift. So why this analysis is key? First, in different communities, the Stokes drift, so some communities have recognized that the Stokes drift is key for the coupling between the lower atmosphere and the upper ocean. And also it can play a key role in the accuracy of scissor-phase variable retrieval from space based on waves observation. But if you parameterize your Stokes drift with the wind speed, you won't take into account the wave current interaction effects, like the current-induced refraction that enhance the significant wave height in some location that have effect on the Stokes drift. So that's something that I want, those 2 key points, like the effect of the spatial variability of the Stokes drift into the accuracy of remote sensing observation on the coupling between the ocean and the atmosphere, are 2 other questions that I want to work on in the near future. So on this very last slide, I want to underscore the pending question that I want to delve into in the near future for application for SWOT, or the effect of the spatial variability of the sea state into the spatial variability of the Stokes drift. So I will be happy to share with you what I have found so far, my material, and if some people want to collaborate on the specific subject, I'm open, but yeah. Now we can move to the Q&A session, I guess. And for people who have to leave, this is my email address. So feel free to contact me afterward. Thank you very much.
Thank you. And questions for Gwen? Maybe while people are starting, I'll ask a really basic question. You showed background currents. What's your source of large-scale background currents? Maybe you said, but...
For this experiment?
Yeah, for these
this is
figures.
HICOM. This is HICOM.
How sensitive is that to the choice of background current? You could use HICOM, you could use glob current or something else.
So that's something that I analyzed during my PhD. So the intensity of the significant wave height gradient are strongly related to the effective resolution of the background current. So here we have observation. So those are, there is no analysis based on the background current here. But for example, if you perform a ray tracing to highlight the current-induced refraction, you would see different results according to the effective resolution of the background current, for sure.
Thanks. I see that Roger Samuelson has his hand up.
Oh, thanks. Very nice talk. Interesting work, Gwendal. I had a couple of questions. One's about this slide. In the right-hand panel, you have U-Stokes, and you. So I'm wondering, how did you actually get that? Is that's computed from the wave observations using linear theory, or is it directly observed in some way?
Okay, excellent question. So what we have, actually, I don't have the location of the observation. Oh, I do. So, up. So this is the observation that I use for the stock drift analysis. So every dot is one wave spectrum. So from wave spectrum, you can compute different wave properties like significant wave height, mean period, and also the Stokes drift. So for every spectrum, I computed a Stokes drift, and then I use my objective maps routine on this on those Stokes drift. So it's based on the Burke formula of the Stokes drift, which depend on the wave steepness. So based on wave spectrum.
Okay, great. Thank you. I had another question, but maybe someone else should go first.
I see that Ad also has his hand up, so maybe we'll let Ad go and come back to Roger.
Yeah, that's fine with me too. Thank you. Hi, Gwendal. Very nice talk. I was wondering, of course, about the winds. So you don't use wind measurements like we have from ASCAT. We also know that models tend to be rather smooth on the scales that you are investigating. And for sure, there are interactions between the sea state you're showing and the underlying ocean and the winds that will impact some of your conclusions, I would say.
Yeah, definitely. And that's something that we have seen with cell-drone observation during the SMOD campaign. So we do see some sub-mesoscale patterns of significant wave height that are associated with an enhancement of the wind as well. But in the mesoscale range, the dominant effect is the current-induced refraction on the current-induced wave action advection. But sure, yeah. So I didn't look at high-resolved wind for this experiment, but from the mass package, so the package that carried the Airborne LiDAR, among others, we are able to have wind observation as well. So perhaps there are some location where the Stokes drift is modified that is associated to an heterogeneity of the wind as well. Yeah, sure. Excellent point.
Yeah.
Okay, well, should we let Roger go ahead with his second question? Anybody else, please raise your hand.
Okay, thanks. Yeah, this is a question about the first part of the talk. And it's actually more a question about the core algorithm than about your results. But at the top, you mentioned the importance of the sea state gradients on the air-sea fluxes. And so I'm just wondering if you just take for granted, say, the core 3.5 algorithm that is wave-based rather than wind-based, how much of a difference in the fluxes, say, of momentum do the gradients that you observed make? Is it more or less a linear dependence on the sea state, or is it quadratic in the way that the wind dependence normally is?
That's an excellent point. That's something that we want to look at with VR. So we had a grant from NASA to look at the coupling between wave current on wind current on waves, and to look at those different effects and the different parameterization. But so far, I have no idea.
Okay, great. Thank you.
So watch this space, I guess. Other questions?
I'll look forward to hearing more in the future.
Yeah. Thank you for your questions.
I wondered about the first part of your talk. You showed results that came out of airborne measurements and the impact of pretty rapidly evolving wave groups and currents that you said changed over 3 hours. What are the implications of all of this for satellite observing systems where measurements might at best come once a day or maybe twice a day, 12 hours apart?
The good thing with satellite is we have a kind of instantaneous observation of the sea state. For example, there is a good example with the HS from SWOT, for example. So here. So when you have an instantaneous observation, you can assume that your background current is stationary. So that's a good. This is a good thing from satellite, but the good thing with the airborne LiDAR is the accuracy of the observation. But yeah, so we have, when we think about spatial variability of anything, like especially waves, because wave depends both on current, on the wind, and the current and wind can change spatially and temporally. We have to be very yeah, we have to be very cautious about those temporal and spatial variability. And the good thing with satellite is this instantaneous observation, but the question is, how accurate are the satellite observation? But we can do some multi-platform comparison to have a first guess of what looks like the background current, for example, when we investigate the spatial variability of the sea state from airborne LiDAR. But yeah, we have to keep in mind that the framework provided by the airborne LiDAR and the framework provided by altimeters, SWOT, or the satellite is different, especially for because of the temporal scales.
Thanks. I see Cesar Sovash has his hand up.
Yeah, hi, Gwen. I thought good to see all your work.
We've lost your sound.
Oh, you lost my. Is that any better?
That's good. Yeah.
Great. Okay. Yeah, great talk, Gwen. Good to see all the work. Yeah, one question that Roger stole. I was really interested in like how does that translate to like surface roughness modification and like fluxus modulation. So yeah, I'll be looking forward to to your new future results. I had another quick question. I was wondering if you looked at like the modulation of like the direction between wave and currents, and how does that affect like the wave modulation, if any?
I didn't, but yeah, I remember. I know why you asked this question. So I remember your talk at Ocean Science. So no, I didn't, but for sure the relative direction between wind, current, and waves would impact the intensity of the sea state gradients, especially for refraction, because the refraction depends on the relative angle between the two systems, among others. So it would have an impact. For example, a good example is the Aguilas current. For example, when you have a specific incident angle, the wave's action can be trapped within the main Aguilas branches, like the southwestward branches, among others. This relative angle between the current and the waves would allow this trap effect or not. So yeah, this is a key parameter that we have to take into account as well.
That's cool. Thanks.
Thanks. Any other questions? I'm sure people have lots of questions. I guess I have one more question I'm going to ask, which is that in some of the SWOT discussion, people have pointed out that SWOT is designed to filter out or smooth over waves shorter than some length scale, around 500 meters. But there are waves showing up in SWOT data that are longer than that, 1 kilometer or longer. What impact is that having Do you have any views on that? I'm just asking in general.
Yeah, I do have in mind also the very cool result highlighted by Fabrice on Breast people. I don't know, but I'm pretty sure that that's something that we can leverage from SWOT observation to better understand the wave dynamics for sure, but also the interaction, the modulation of the C state in the meso-to-submesoscale range. But I don't know actually, but yeah, I think we are very glad that NASA and CNES created this 250-meter product. So, so when with the sentence, the SWOT doesn't resolve waves, but depends on the C state. Actually, when we have very long swell, as you said, we do resolve waves.
Yeah, so we'll see what we learn from it, I guess.
Yeah, but I don't know. But yeah, promising.
Okay, well, if there are no further questions, thank you very much. This has been great, really interesting, and we'll see everybody next week.
Thank you very much. Have a good day.
Thanks a lot.